We have a hollow cylinder that's aligned with the z-axis, and it has a radius of a. And on the outer wall of the cylinder, a sheet current density is flowing of magnitude k sub z and in the direction a sub z. Now we can think of the current flowing as a collection of current filaments lined side by side around the cylinder. Okay, so now what I want to do is take a view looking down the z-axis. So in other words, we're going to take a look at a cross-section of the cylinder looking down the z-axis. Okay, so here's our cylinder with radius A, and you can see the current filaments lined up to form our sheet current density that's flowing up in the A sub z direction. So we're going to first consider the case of rho where rho is greater than A. So let's look at one current filament and the magnetic field intensity that it generates. So we're going to look at this current filament right here. So the current is flowing up out of the page. So we know if we put the fingers of our right hand, our thumb of our right hand in the direction of the current flow, our right fingers will point in the direction of the magnetic field intensity lines which will form these closed circles around the filament. So now if we look at this current filament right here, the magnetic field intensity lines will form closed circles around it like this. So now let's go to this point outside the cylinder and look at the magnetic field intensity lines from these two current filaments that are symmetrically on the two sides of the cylinder from this point where we want to find our field. So this is the magnetic field intensity generated by this current filament, and this is the magnetic field intensity generated by this current filament at this point. Okay, so the direction of the magnetic field intensity at this point due to this current filament is in the direction of this tangent arrow to the circle at this point, and the length of the arrow represents its magnitude. Similarly, this tangent arrow here represents the direction of the magnetic field intensity due to this current filament at this point, and again the length of this represents the magnitude. And since the two lengths are the same, and from the geometry we see that they will sum and give a magnetic field intensity that's only pointing in the A sub phi direction. And so what we can do is use superposition and just keep taking pairs of current filaments like this all around the circle and computing the corresponding magnetic field intensities and summing those, and we would find then that the magnetic field intensity at this point due to the cylinder is h sub phi rho in the A sub phi direction. And because of the cylindrical symmetry, we would get that result at any point we would go. If we went and summed up all the contributions to the magnetic field intensity due to all these filaments, the field at any point would be in the A sub phi direction. So we've just argued that the magnetic field intensity lines outside the cylinder will be these closed circles that are centered on the cylinder. So the form of these will be h sub phi in the phi direction, and the magnetic field intensities will not depend on phi because of the cylindrical symmetry, and also it won't depend on z because we're assuming the cylinder is of infinite extent in the c direction. So the only variable it can depend on is rho. Now that we know the form of our magnetic field intensity for rho greater than a, where a is the radius of our cylinder, we're going to apply Ampere's circular law that the integral of h dot dl is equal to the current enclosed. The Amperian loop we're going to pick for our path of integration is going to be a circle of radius rho centered on our cylinder. So let's pick the direction of our integration as counterclockwise. Okay, so the integral of h dot dl is equal to the integral of the form of our magnetic field intensity. It only has a component in the phi direction, and it will only depend on rho, and we dot it with dl. In cylindrical coordinates, dl will be the following. If you change rho by an amount d rho, you move a distance of d sub rho in the a sub rho direction. If you change phi by an amount d phi, you move a distance rho d phi in the phi direction. And if you change z by an amount dz, you move a distance dz in the z direction. Okay, so looking at distributing these terms, a phi dot a rho is 0 and a phi dot az is 0. A phi dot a phi is 1, and that will be the only term we're left with. So this dot product reduces to the integral of h sub phi times rho d phi. Now, doing the path integral around this Amperian loop here, rho is being held constant, and because rho is being held constant, the magnetic field intensity in the phi direction is a constant. So these two terms can be moved to the left of the integral. And so we just have an integral of d phi. So to move around the closed path, phi will change from 0 to 2 pi. So the integral of d phi from 0 to 2 pi is just 2 pi. So our integral becomes 2 pi rho times our h component in the phi direction. Now, this is going to equal the current enclosed. Now, we know the sheet current density around the cylinder. It's K sub Z amps per meter. So we need to multiply that by the distance around our cylinder, the circumference of the cylinder, which is 2 pi times A. Okay, so this will equal the current enclosed being 2 pi A times K sub Z. So now if we solve for our component of h, we get A times K sub Z over rho. Okay, so for rho greater than A, the magnetic field intensity is A times the sheet current density over rho, and it's in the phi direction. So now we have to address the situation for inside the cylinder for when rho is less than A. We'll see it turns out the magnetic field intensity inside the cylinder is 0. And if you have an Amperian loop inside here, and you take the integral of h dot dl around that loop, clearly the current enclosed by that loop, that is the current through this surface, is 0. Now, it's wrong to conclude that because of this, H is equal to 0. Because we know H is not 0 outside our cylinder, but if you took a path like this, integral of H dot dl around that path is going to be 0 because there's no current enclosed, but there is a magnetic field intensity at every point along our loop. So we need a different argument to come up with to see that the magnetic field intensity is 0 everywhere inside our cylinder. So let's consider this point here inside our cylinder. So this vector here represents the magnetic field intensity at this point due to this current filament, and this vector here represents the magnetic field intensity at this point due to this current filament. And so from the geometry we see those will add and give an overall contribution to the magnetic field intensity represented by this vector pointing to the left. Now, if we move to another pair, like these two right here, we would see that the magnetic field intensity at this point due to this current filament is represented by this vector, which is longer than the vectors here because we're now closer to the current filament producing that magnetic field intensity. And this magnetic field vector represents the magnetic field intensity at this point due to this current filament. So these two are going to add to give a component pointing to the right. As you sum up the contributions to the magnetic field intensity at this point due to each set of pairs of current filaments, you find the result is the field is pointing either in the A sub phi or the minus A sub phi directions. So you can conclude that the magnetic field intensity inside our cylinder only has a component in the phi direction, and because of the symmetry will only depend on rho. So now we're going to apply Ampere's circuital law to this Amperian loop. So dl will be rho d phi in the phi direction, and h will have this form here. So a phi dot a phi is 1, so here is our integrand, and the current enclosed here will be 0. So rho is a constant on our Amperian loop, so we can remove rho and h to the left of the integral. So this integration will give us a 2 pi, and the only way for this result to equal 0 is if our magnetic field intensity inside our cylinder is actually 0.